Hi, good evening. This is Tariq Rashid, class Artificial Intelligence Neural Network Part 3. Um, this In this part, I talk about single artificial neuron. The basic neuron was formed by McClock and Pitt in 1943. It's a basic computational unit, cell. But the real power of neural computation emerges when neurons are connected into networks. So one neuron cannot do much. Neurons are indexed by IJK for each layer, input, hidden, and output layer, respectively, and connected through synapses. Synaptic weight um, represents the strength of connection from neuron I to neuron J. One neuron can't do much, as we said. Usually, we will have many neurons labeled by indices K, I, J, and activation flows between them via connection weights. Now, input layer contains neurons of McClock-Pitt, and there is a direct connection to an output layer, and there is no hidden layer. It's a single uh, uh, layer perceptron. So this is McClock-Pitt. You've got inputs, uh, so many inputs, and they will sum up with weight connection. So inputs multiplied by weight, that is summed up I0 to J, for example. I equals, for example, J or K or N, doesn't really matter. So, and then they will be subject to activation function, and the output will go to the next layer in the network. This single layer perceptron, the first layer cannot be considered as a layer. It's processing layer, inputting layer, and there's a sign function. There's a threshold to see whether this input will be positive or negative. Now, basic gates, we have NOT and O, and these gates form a functionally complete set. Now, if we have sigma Wi and xi sub I, so that is your net, and minus theta, that's your threshold. So if this net greater than theta or equal, then that's positive. Otherwise, it's negative. So we have a NOT gate. That means we have only one input. If we put 0, then we get 1. And if we put 1, then we get 0. AND gate or OR gate, we have 0, 0 gives you 0, 1, 0 gives you 1, 0, 1 gives you 1, and 1, 1 gives you 1. So this is more flexible. So 3 ones you have. Here we have 3 zeros. So the only condition that gives you 1, 1, you should have 2 inputs. Each one of them got 1. So let's do it. If we have 0 here, multiplied by, that's I, multiplied by weight connection, which is minus 1. So 0 multiplied by minus 1, minus 0 multiplied by minus 1 is 0. 0 less than 0.5, that's no, then it means not, it means 1. And then if we put 1, 1 multiplied by minus 1, that would be minus 1. Minus 1 is greater than 0.5. That's not, then it'll be 0. So that is for NOT gate. Let's do the O gate. O gate 0, 0. 0 multiplied by 1. 0 multiplied by 1 plus 0 multiplied by 1. That's first one. And 0 multiplied by 1. That is second one. So altogether 0. 0 less than 0.5. Yes, 0 is less than 0.5, then the result is 0. Let's do one more example. Let's do 1, 1. So 1, 1. 1 multiplied by 1 plus, that's 1 multiplied by 1, and 1 multiplied by 1 plus 1 multiplied by 1. So 1 multiplied by 1, 1, plus 1 multiplied by 1, 1, 2. 2 greater than 0.5, yes. 2 greater than 0.5, yes. That means we say it's greater than threshold, it's 1. So the answer is 1, correct. So that's for OR gate. And let's do the AND gate, one example. Let's take this example for AND gate, for example, 1 and 0. So, 1 and 0. So 1 multiplied by 1 multiplied by 1, 1 multiplied by 1, plus 0 multiplied by 1, 0 multiplied by 1. So that is 1 multiplied by 1, plus 0, 1. So 1, that's the result 1. The result 1. 1 is greater than 0.5? No. Then the output is 0. So the output is 0. That's for, you can see the AND gate, we have 3 zeros results and 1 AND gate. So we can have a hyperplane that separates the two data. That's 1. These are zeros, 3 zeros that we have. So 2 sets of data. And or we have 3 ones and 1 0. So we can easily make a hyperplane because they're all on this side. And all zeros are on the other side. Now let's do XOR. XOR is difficult because 0, 0 gives you 0, 0, 1 gives you 1, 1, 0 gives you 1, 1, 1 gives you 0. So this is kind of difficult to do it. And I tell you why to do it, because there is a problem. You can't have a compatible equation for this one. So let's plug in, these are the inputs for AND. 0 multiplied by W1, that's 0 W1, and 0 multiplied by W2, 0 W2, minus theta. So take theta to the other side, it will be theta greater than 0. And likewise, 0 multiplied by W1 and 1 multiplied by W2, and that's how you get these two equations. Likewise, 1 multiplied by W1, 0 multiplied, and minus theta, take it to that one, it will be W1 greater than theta, less than theta. So W1 plus W2 greater equal theta. Can we just prove this one is correct or not? Let's assume that theta is 0.5 and W1 is less than theta. Let's call 0.3. W2 less than theta. W2 is 0.2, and or 0.4, let's say, still less than theta. So W1 plus W2 should be greater equal theta, and theta is 0.5. So W1 was 0.3 plus 0.4. That is 0.3 plus 0.4, 0.7. So it is greater or equal 0.7. That's correct. So this equation correct. Now, limitation of XOR. Here, W1 0 multiplied by W1 and 0 second input multiplied by W2. So theta, take it to the other side, it will be theta greater than 0. Likewise, 0 multiplied by W1 and 1 multiplied by W2. Then theta, take it to the other side, then W2 greater equal theta. Likewise, 1 multiplied by W1, 0 multiplied by W2, and then minus theta, then W1 greater than theta. So let's assume that theta is greater than 0 in the first equation. So theta is 0.5, we assume. Now, W2 greater than theta, we can put a 0.6, greater than theta or equal. And W1, again, greater than theta, we can say 0.5, greater or equal theta, 0.5, 0.6, 0.7, or 0.9, as long as greater than theta. Now, let's see this equation. W1 plus W2, so it is 0.6 plus 0.5, W2, 0.6, W1, 0.5, smaller than, according to equation, 0.5, theta. 0.5 is theta. So 0.6 plus 0.5, it'll be 1 point something. So that is wrong. This cannot be satisfied. So there's inequality. W1 plus W2, it's greater than theta, not smaller than theta, from the assumptions that we made. So that is the problem. And the problem is that we have 0, 0 is 0, and we have 1, 1 is 0, two classes, and we have 1, 0 is 1, and we have 0, 1 is 1. Here, the problem is that we have two classes, and there is no one hyperplane can divide or segregate these two classes. So that's the problem of XOR. So thus we can say that single layer perceptron, single layer neural network cannot solve XOR problem unless we have another solution for it. And another solution is that we need to get multi-layer perceptron. So that's hidden layer, that's input layer, and this is hidden layer, and this is the output layer. So now you have 3 layers, 1, 2, 3. It's not single layer perceptron. Or we change the activation function from sine to sigmoid or tangent. Now let's try to test this network. These are selected weights, 1, 1, 1, 1, 1, 1, 1, 1 minus 1. So, and let's feed in first input. The first input is 1, 1. So 1 here, 1 here. So 1 multiply for this neuron, 1 multiplied by 1, this 1 multiplied by 1, 1 multiplied by 1, plus 1 multiplied by 1. So it's all together. 1 multiplied by 1, 1. 1 multiplied by 1 is 2 now. This neuron is 2. 2 greater than 0.5, yes. So the output is 1 here. Now let's do this side. 1 multiplied by 1, 1 for this neuron. So we do this and this. 1 multiplied by 1, 1, plus 1 multiplied by 1, 1. Again, this is 2. 2 greater than 1.5, yes. So the result is 1 here. So now we found the net out of this neuron, first one, is 1. And the neuron of second one is 1. So now 1 multiplied for this neuron, 1 multiplied by 1, it is 1, plus 1 multiplied by minus 1, 1 multiplied by minus 1. So 1 multiplied by 1, 1, 1 multiplied by minus 1, minus 1. So 1 minus 1 is 0. So 0 smaller than 0.5, 0 smaller than 0.5. No. Therefore, the result is 0. That is done. Now we can take 0, 0. Again, check 0, 0. If we feed 0, 0, 0 multiplied by 1 for first layer, and 0 multiplied by 1 for So it is 0 altogether. So this is 0. And if we have 0 here multiplied by 1 is 0 for the second neuron. And 0 multiplied by 1, 0. Now, um, here we have that is 0 multiplied by 1, 0 multiplied, that's 0, 0, that's 0. That's also 0. So 0 multiplied by 1, that's 0. And 0 multiplied by -1, that's 0. So 0 greater than 0 greater than 0.5. No, that means the result is 0. So we did 1, 1 was 0, and 0, 0 was 0. So that is the idea of this one. This network fulfills um, XOR gate. The rest I will leave it for you. So thank you very much for listening, and hopefully we will have a next part of tutorial on neural network. Thank you very much.